Hello and welcome in this nicely dry shelter. We will now witness a presentation by Non Sequitur and A-Band about hardware hacking for software geeks. Basically on which end to grab your soldering iron when reverse engineering embedded devices. Have fun.
Hello. Before we start, I'm going to have to make a request that you hold questions until the question and answer period, because our monitor is unplugged so that we could plug in some stuff up here, and it makes it hard to hear things coming from the audience.
All right, our talk is hardware hacking for software geeks. The purpose of this talk is to help people who have written applications but maybe haven't worked much with hardware to know where to start. I mean, you have a device, you may not, or you know what it does, but you may not be able to interoperate with it, or you want to change how it operates. And this is a starting point. So we're going to go over how to set up a lab, how to design your own embedded devices, and then how to reverse engineer someone else's embedded devices, because those things are all interrelated. If you don't know how devices are designed, there's no way you're going to be able to reverse engineer anything without knowing the common design patterns that embedded devices share. So,
I have a lab in my home, and I found it immensely useful for aiding my work because it provides a space where I can, when I'm in that space, I know that I'm there to hack. It's not my bedroom or my kitchen or a space that I use for other things. Initially, I had about a 12-foot by 12-foot room, but I've since moved and now have 15 by 20 feet, and that's for one individual. Most of it's given over to storage. It's in a basement, so I've had to add an exhaust fan for ventilation. Good ventilation is key if you're working with hobby electronics a lot, because soldering, etching circuit boards, sanding the edges of circuit boards even, release chemicals that you probably don't want to inhale. A particularly bad example is the etching process, which tends to release either chlorine or very pure oxygen, depending on what process you're using, which is very hard on your lungs. You want the area to be well lit so that you can see what you're doing. Brighter light will cause your pupils to become small, which actually does help your focus. You generally want work lighting, which is to say the light needs to be located above the work, not in the center of the room, so that the light is cast on what you're working on and not the back of your head.
another important thing is grounding and ESD. That's a term that if you ever are in a commercial hardware lab, ESD is a big deal because it means electrostatic discharge, and it can very subtly damage an electronic board, and it most likely it's not going to fail immediately. It will not work in a way which won't appear for months possibly, but it will be broken and cause the device not to operate properly. I mean, it's going to appear to be working, but there's a lot of things you can do to prevent this from happening. And the reason you do this is so you have control, and you eliminate one extra variable. So when it doesn't work, you know it's your fault, not the board's. And you can get grounding mats and the wrist bracelets that you ground yourself so you don't shock the board and take out a component. And another thing, if you have pets, you want to get an ESD coat, because the material of the coat prevents a static charge from forming on the hair from the pets. And then if the hair touches the board, it won't shock the board either. So if you have lots of cats or a dog that's long-haired, ESD code is probably a good idea if you want to work with sensitive modern electronics.
If you're going to be doing any hardware modifications, you probably ought to learn to use a soldering iron. How many people here have any experience with soldering? Okay, a good number. I don't want to talk down to people too much, but for the people who haven't had any experience in it, how many of those people know what it is? Okay. Soldering is the process of attaching electronic components or other metal pieces together using a molten metal. Usually an alloy of tin and lead, although recently the RoHS directives have forbid the use of lead in a lot of consumer electronics. The tool for soldering is a soldering iron, which is basically a piece of metal that's heated electronically to melt the solder. The solder is just essentially looks like a very soft metal wire, but it contains a core of a flux, which is a material that when it burns in the heat of the soldering iron, cleans off the parts that are being soldered together with a caustic vapor. This vapor is another reason to have ventilation in your lab. If you inhale it for very long, it causes headaches, dizziness, and a variety of other unpleasant symptoms.
You also want to select the right solder. I've destroyed a couple boards because when I first started off, I didn't have anyone there to teach me, and I got a solder which was too thick of a gauge and an iron that didn't have a fine enough tip, and I was globbing solder all over the place, and when I tried to fix it, traces would come up, and I learned the hard way that you want to get the stuff that says electronic solder. It's a very fine gauge, and maybe a 20-watt tip for soldering and a 40-watt iron for desoldering connections. Another tool which is useful is a desoldering wick or bulb for removing solder, either from your own work or to free up a port that's been closed through wave soldering when they were attaching the PCB assembly to the PCB board.
Another point of solder selection is the metal composition. The most common is 60% tin and 40% lead, I believe. I may have the numbers backwards, but it's marked as 60-40 solder. The lead is, of course, lead and is poisonous. But it makes the solder much, or at least I find it easier to work with. If you don't want lead, there are lead-free solders available. Usually they'll have somewhere around 2 to 5% silver in them as well. It makes a slightly harder solder, and I don't find that it wets as well, which is to say it doesn't seem to bond as well to the parts, but it is lead-free, and so you don't have to take typical lead handling precautions. That's not good.
No, it's not.
We have a little problem with the slides. Modern electronics packages can be very difficult to solder. There are packages such as ball grid array packages, which consist of, instead of pins coming out of the side of the component, an array of very small solder dots all over the bottom of the component. When the component is resting on the board, there's no tool that can reach under it to solder those points, so they have to be soldered by some other method. Generally, that's heat applied via either radiant heat from an oven or directed hot air from a hot air gun. These are some techniques for doing it in your home. In a commercial setting, they would usually use a hot air oven or a soldering oven, which has a computer-controlled temperature settings and usually costs $2,000 and up. Obviously, for the home hobbyist just getting into this, that's not practical. Toaster oven reflow soldering uses a typical toaster oven like you would find in your home. The Viennese camp, I believe, was actually using one of these to solder controller boards for a LED display that they're making. Essentially, the part is held down using a paste that is the solder dust, like as a metallic dust, combined with a liquid flux. That's applied very carefully to the places where the solder is needed. the part is set in that paste, and then the entire assembly is baked. As the temperature rises, the flux burns away, which results in the parts being cleaned by the flux vapor, and then the solder itself melts. The surface tension of the solder is sometimes sufficient to align the parts precisely, but generally you want to be as precise as possible when placing them. There are kits available to build temperature controllers for toaster ovens, and the kits are very inexpensive, less than $50 American. Another technique is to use an electric skillet. It's the same general idea, applying a gradually rising heat to the board, but in this case the top is open so the ventilation is easier and you can watch the progress of the soldering. You'd never want to do this and then immediately cook your breakfast on the skillet. Like I said, dangerous chemicals everywhere. Hot air tools can be used both for soldering down electronic components and for removing them. I recently had an opportunity to do this in the Hack Center when removing a 25-pin connector that had half of its pins soldered down. Since there was no way to heat all of them at once using a normal iron, we borrowed a hot air tool. This is a homemade hot air tool. What basically happens is air is pumped through the handle and then through this heating element. The air then hits whatever part is being heated and eventually melts all the solder joints in the hot air blast. This can be used to desolder entire microchips at once, which is very convenient if you're salvaging from deceased pieces of electronics. And is also useful if you find out that you've made a mistake and don't want to desolder 30-some pins by hand.
Other tools are a good multimeter, which has a volt ohm meter on it, analog or digital oscilloscope, which can read signals, and a logic probe or a collection of logic probes, which is known as a digital logic analyzer. Now, those can either be home built, or you can purchase cheaper USB versions online. Or if you were to be working in a commercial lab, the same equipment can cost anywhere from $5,000 to $50,000 and up for the good high bandwidth equipment for doing work with modern general purpose processors. But for our purposes, we're not going to be working with anything over 40 megahertz today. So something with 50 megahertz of bandwidth is more than sufficient.
A commercial logic analyzer, can everyone hear me?
You got to get your mic closer.
Back a little bit.
Nope.
Hello? Okay. A commercial logic analyzer is typically a PC running a full-fledged operating system with specialized data acquisition hardware on it. I have one at home that doesn't quite work yet, but it's about the size of that suitcase and brand new, cost around $10,000, I think. Obviously, I didn't buy it for that price, or I wouldn't have been able to afford to come here. A volt ohm meter is one of these devices. It basically just displays voltage, current, resistance. This one also has a diode check function, which can tell you if a diode is blown or not.
Well, multimeters also can have things like frequency analysis. If you've got a pulse width modulated signal, you can put it into a frequency analysis mode, and they'll give you the hertz or the frequency of that signal. And there's lots of functions that they can put into the more advanced ones.
Some of them also have capacitance and inductance measurements. There are some that have a thermocouple that you can hook up to it to measure temperature. All these features, of course, add to the cost. This one, mine, is fairly basic, has lasted a good number of years, and has some features I don't even use, like a serial port in the top.